We're finally doing it. We're talking about the antiderivative. This is the major topic for the rest of the course. Most of what we've done so far has been the derivative. We're going to change gears a little. If you got sick of the derivative, maybe this is a chance for a fresh start. The antiderivative, it's different from the derivative. It's very closely related, but it's not the same. The idea behind the antiderivative is this. We say things like the derivative of x cubed is 3x squared, right? The derivative of x cubed is 3x squared. The antiderivative is just the other way around. If the derivative of x cubed is 3x squared, the antiderivative of 3x squared is x cubed. It's like the opposite operation. So it's like, multiplication. The inverse operation to that is division or addition. The inverse of that is subtraction. Antiderivative is the same way, but with the derivative. So we say, in this case, the antiderivative of 3x squared is x cubed. All right? How about another example? The antiderivative of 2x is... You got to think, what is a function whose derivative is 2x? Do you know a function so that when you take the derivative of that one, you get 2x? I think you do. X squared is a function whose derivative is 2x, right? Actually, there's a bit of a subtlety when you're doing antiderivatives. X squared is not the only function whose derivative is 2x. Can you think of another function whose derivative is 2x? It doesn't have to be x squared. Another function whose derivative is 2x? How about x squared plus 1, right? Because when you take the derivative here, you get 2x from that part and this part disappears. So I guess x squared plus 1 is also an antiderivative. There's not, technically speaking, there's not the antiderivative. There's different ones, but they all basically look like x squared. They just could have plus something else, or it could be, x squared minus 8. It could be x squared together with any constant. X squared, and I'll write it as a plus, although it could be a minus if the constant itself is negative. X squared plus c, where c is any constant, all right? This is a pain which hopefully you will get used to. Every time you do the antiderivative of anything, you will always write plus c at the end. That's just the way it goes, because antiderivatives are not unique, right? Given one thing, there's always different ways that you could make antiderivatives. They just differ by constants, though. How do we write all of these things? I'm not going to write out the word, the antiderivative of blah, blah, blah equals whatever. The antiderivative, what I just wrote, the antiderivative of 2x is x squared plus c. We write it this way. Integral sign 2x dx equals x squared plus c. So this is like a weird looking S, sort of a long and tall S. This is called the integral sign, and this, together with the dx, indicate the antiderivative. It's a little strange that the antiderivative is written sort of in two pieces. You put the function in the middle of these two things, the integral sign and the dx. This is written as if you're multiplying by dx, which is a little weird. This dx is not actually a thing that you are multiplying by anything. It's just part of the way that we indicate what the antiderivative is. Why do you even write with a multiply by dx? It's because, there's actually a few reasons for this. This is not really as weird as it seems, but when we write the derivative, we write it as if it were a division by dx, and so it is natural in that sense to write the antiderivative as if it were a multiplication by dx, because it's meant to be the opposite of the derivative. Anyway, this is how we write it. This weird-looking s is called the integral sign. The antiderivative is also known as the indefinite integral. So we are often going to use this word integral as sort of a synonym for the antiderivative, although there is such a thing as the definite integral, which we're going to talk about a little bit later. Specifically, the antiderivative, it's called the indefinite integral. The definite integral, we write similarly, but it means something different. All right, so this was one example. The integral of 2x dx is x squared plus c. Also, the other example that I said before, the antiderivative of 3x squared, the integral of 3x squared, is x cubed plus c, right? This means that a function what is a function whose derivative is 3x squared? The answer is x cubed plus some constant. The constant could be anything. All right? There's some examples. Here's a less clear example. How about that? The integral of 3x dx. The antiderivative of 3x. What is that going to be? You know, for 2x, we used x squared because x squared, when you take the derivative, the 2 comes down here. So when you do the derivative of x squared, the 2 comes down in the front, and then the exponent here decreases to 1, and you get 2x to the 1, right? How can I choose this function here so that instead of 2x to the 1, I get 3x to the 1? That's what I want. Well, if you change the exponent to a 3, actually, that doesn't do it. That puts a 3 in the front, but it screws up the exponent. Here's the trick. I'm going to use the exponent of 2 anyway, because the exponent of 2, when I take the derivative, this will decrease the exponent to a 1. And I'm just going to mess around with the constant in the front. If I put, here's the trick, 3 halves here, and then plus c, of course, you always put plus c. Then I think you will agree, if I take the derivative right here, the 2 will come out front, cancel this 2, and I'll end up with a 3 coefficient times x to the 1, which is exactly what I want over there. All right, that's how we do it. Actually, you can do this in generality, just for any power of x with perhaps a constant in front of it. Can we say, let's not focus on the constant in front. What is the integral, the antiderivative of x to the power n? If you have any power of x, remember to do the derivative in this case, we use what we call the power rule. You do this all the time. It is n(x to the n minus 1, right? Where the strategy, what you do is you multiply the exponent in front, and then you decrease the exponent. If I want to reverse that process, I should, instead of decreasing the exponent, I should increase the exponent to do this backwards. And then I should, instead of multiplying in front, I should divide in front. So the way this works is like this. You increase the exponent and then divide by the new exponent. All right. This will always work. If you put, x cubed in here, what do you get on the right side? You get x to the 4. Well, I might as well just write down what I'm saying here. What is the antiderivative of x cubed dx? What you get is 1 over 4x to the 4, right? You increase the power by 1, and then you divide in front by the new power, and then plus c, of course. One nice thing about antiderivatives, you can always check your answer at the end by taking the derivative over here, and you should end up with x cubed. Let's just see if it works. So check it. Take the derivative of the answer. Derivative of 1/4 x to the 4 plus c. When I take the derivative of 1/4 x to the 4 comes out front, cancels with the 1/4, and I'm just left with x to the 3. And then the derivative of the c, constant, the derivative of a constant is always 0. So yeah, it worked, right? I got what I see in there. Okay, this right here, this is the power rule for antiderivatives, and you definitely need to memorize that. Although, you're going to be doing this over and over again, so you will just naturally memorize it. I don't think you'll ever have to sit down and memorize that as a formula. You're going to do this all the time. Let me just say one thing about this. It works for all n's. It works even for n's being fractions or positive or negative, whatever. Except there is one value of n for which this formula does not work. And you can tell, if you look on the right-hand side, we see n plus 1 in a denominator. That means automatically this cannot work if n is -1. Because if n is -1, then this will have a 0 in the denominator. So this, I'm just going to say this works. This works for all n except n equal -1. There must be a special rule for this one, x to the -1 power, right? Also known as 1 over x. That's what -1 power means. So when you have powers of x, you always use this formula, except there is one special case, a very special, exceptional case. It is this. What if the exponent is -1, which is the same as saying, what if the function is 1 over x? Well, there is an answer. I'm not saying you just can't do that one. There is an answer. It just doesn't look at all like this. You have to cast your memory back. Have you ever seen what this question is asking is, what is some function whose derivative is 1 over x? Is there such a thing? Actually, we have discussed such a thing. Do you remember the function whose derivative is 1 over x? There is such a thing. It is the natural log of x. This is one of our, things that we talked about. In fact, the most general way to say this is the natural log of the absolute value of x. Its derivative is 1 over x. So what that means is the integral 1 over x dx equals natural log absolute value of x plus c. So put this in a box somewhere and memorize that also. This completes the rule of the power rule, right? The rule with the x to the n from before, that works whenever the n is not -1. When the n is -1, this is the rule that you use. All right? That covers everything in terms of powers of x. Let's also talk about another very simple type of function would be if I just have a constant inside here. Like, for instance, what is the antiderivative of 7? What you should be thinking is, do I know of a function whose derivative is 7? And yes, you do. It is 7x plus c. So generally speaking, if you have just a constant, then the result, the antiderivative is that same constant times x. All right? This kind of goes together with that power rule. If you have just a constant all by itself and take the integral, you get that same constant times x. All right, we got rules. Rules for the antiderivative. Now, these are rules for the derivative. I hope that you remember these rules. These are rules that you probably by this point don't even think about them anymore, but you do these all the time. When you're taking the derivative, the first one says if you have a bunch of stuff added together and you're taking the derivative, you just do the derivative of each of the things that are added together. You do that constantly. And the second one says if you take the derivative of a constant multiple of something, the constant multiple just stays on the front, and then you do the derivative of the other part. We do this all the time. So these two rules, because of the way that the derivatives work in this way, these two rules automatically tell you that the same must be true of the antiderivative. If you just sort of read the rules backwards, the same rules are true of the antiderivative. So what that says is the integral of f of x plus g of x dx is equal to the integral f of x dx plus the integral g of x. This means when you take the integral of something, some bunch of stuff added together, you can just go down the list and take the integral of each one. And also, the integral of a constant times a function dx is equal to, that same constant can just sit in front of the answer of the function that you're taking the integral of. So if you do have an extra constant multiple, you can just leave that as a constant multiple in front of the answer of the antiderivative. All right, these are also super important in the category of you definitely need to memorize these, but you're going to do them so often that you won't even have to think about memorizing them. Let's just do a simple example that uses these guys. Examples. I got examples. Here's an easy one. Now, what I see here is a bunch of stuff added together. That means we can just go down the list here and do the integral of each one. And what are we going to get? We get, if you like, I'll break it up this way. 3x squared plus integral, really this should be like that. All of this is inside the integral with the dx. But when I break it up, I go 7x dx. And I go plus 8, integral 8 dx, right? And then, so that was using the first rule that I just said about adding stuff together. And then we can factor all these constants out. 3 integral x squared dx plus 7 integral x dx plus 8 integral dx, I guess. That's a little weird, but anyway. What do we do now? 3 integral x squared. Well, I can do the integral of x squared. Remember what you do? You increase the exponent by 1, and then you divide out by the new exponent. So it's going to be 1/3 x cubed. Plus, the next one has a 7 here. And then here, I do the same trick with the exponents. This is a x to the 1. I increase it to x to the 2, and then divide by the new exponent. So I get 1/2 x squared. And then finally, 8 integral dx. What is this? Integral dx is weird. There's really a 1 there. 1 times dx. And remember, the integral of any constant is just that constant times x. So what I'm going to get is 8x. And then, as always, we put the plus c. Now, you might have been wondering, why didn't I put the plus c every time? Really, there should be 3 different constants all added together, where those constants can be anything. Well, if you have 3 constants which could all be anything, and you add them all together, the result is just another constant which could be anything. So we're never going to write several plus c's. You might as well just combine all of those constants into a single plus c at the very end. This is your answer. If you want, you can simplify a little bit, although I don't care so much about that. These 3's can cancel, right? I just get x cubed. This, maybe I'll write 7 over 2x squared, and then 8x plus c. All right. Now, I wrote this out in several steps, although once you know what you're doing, you can jump to this answer immediately just looking here. What do? You just go down the list here and take the integral of each part, leaving the constants in the front. So this 3x squared becomes 3, I'll leave the 3 in my answer, times 1/3 x cubed, which is that. 7 times x, I leave the 7 in my answer, times 1/2 x squared, which is that. And then 8, the integral of 8 is 8 times x, which is that. So it's very easy to just go from here to here if you once you get used to things. I would not expect you to write all these intermediate steps. I did it just that once. I'm never going to do it again. Another one. Now we're getting serious here. This one is not just a bunch of stuff added together. We have a product on the inside of the integral. Did I tell you how to do the integral of a product? No, I did not. For the derivative, remember, there's a special rule. It's the product rule. We need some kind of product rule for the antiderivative, but it turns out there isn't really one. So the version of the antiderivative product rule is called integration by parts, and it's not something that we're going to talk about in this course. I'm here to tell you, do not try to just do the integral of each of the 2 parts. When you see multiplication in there, it means you got to do something tricky to rewrite things so that there is no multiplication. So I'm going to say rewrite the integral, rewrite the function on the inside to avoid multiplications, because you cannot just do the integral of a product. How can we rewrite this? Well, I'm going to keep the integral sign there because I'm just rewriting what's on the inside. I think you can just distribute the x on the inside, can't you? Distribute. I get x cubed plus 3x dx, right? And now this is something just like the one we just did. This is something you can take the integral of easily. I get, from the x cubed, I get 1/4 x to the 4, because you increase the power by 1 and then divide by the new power. And then here, the power is 1, so I get 3 over 2 x squared plus c. That's how we do it. When you see multiplication inside the integral, you got to do something special in order to deal with that multiplication. And in this case, you just distribute. Not so bad. All right, this one is similar, but it's got division in there. Again, there is no quotient rule that you can use here, and you definitely should not just do the antiderivative on top and the antiderivative on the bottom. What are you going to do instead? You got to somehow rewrite this so that there's no division anymore. Well, my strategy is like this. I'm going to write this again as if it were multiplication by a negative exponent, and then distribute. Kind of like the previous example. It becomes, what do you do in this case when you're distributing? You should be adding the exponents. So this is x to the 1 times x to the minus 2 gives me x to the minus 1 plus, and then distributing here gives me x to the minus 2. And now I take the integral of each of those. What is the integral of x to the minus 1? Usually you increase the power by 1 and then divide by the new power. But here it becomes 0 and you can't divide by the new power. That's because there's a special rule. When it's minus 1, you get the natural log of the absolute value of x. You just have to remember, in the case when the exponent is minus 1, you do something totally different. You get the natural log. Okay, and then this one you can do without any problem. You increase the power by 1, it becomes negative 1, and then I divide by the new exponent. And then, sorry, not dx. I just did the integral, so I get plus c. And that's how we do it. This, if you want, you can rewrite this as log absolute value x minus x to the minus 1 plus c. If you like, whatever. I don't care so much about that. I got more rules for you. What about the antiderivative of exponential functions? I hope, first of all, can I refresh your memory about the derivative of exponential functions? All right, these first two, I hope you remember, or you have them in your notes somewhere. The derivative of e to the x equals e to the x, and the derivative of a to the x, where a is some different exponential base, is a to the x times the natural log of a. These two are important also rules that I think will be helpful to write down. These, probably you didn't write these down before, but this is what you get if you use the chain rule from the first one. E to the kx, when you take the derivative, you get the same thing again, which is e to the kx, but then you multiply times the derivative of the inside, which is k. All right, and this is what you'll get if you do the chain rule on a to the power kx. It turns out these kinds of exponential functions, where you have some constant inside the exponent, are very common in application. So it's useful to write these down as specific rules. All right, what do we get in terms of antiderivative formulas for these? Well, the first one is very easy. The derivative of e to the x is e to the x. That means the antiderivative of e to the x is e to the x. So here's one. Integral e to the x dx is e to the x plus c, right? E to the x, when you take the derivative, it stays the same. That means when you take the antiderivative, it stays the same. What about e to the kx? When you take the derivative here, it stays the same, but you multiply by k. How would I do the inverse of that? When you do the antiderivative, it should stay the same, but you divide by k. You have to do the opposite, right? So the rule for the antiderivative is this. Antiderivative e to the kx is 1 over k e to the kx, right? When you do the derivative, you'd be multiplying by k. When you do the antiderivative, then you better be dividing by k. Okay, and then similar ones for the a's. They look the same, only they have these extra ln a's in them. So integral of a to the x dx is a to the x divided by ln a plus c, right? In the case of the derivative, you multiply by ln a. In the case of the integral, you must divide. And the most complicated one, integral a to the kx dx. In this case, for the derivative, you multiply by ln a and also by k. For the integral, you should divide by those things. It's a to the kx over k ln a plus c. All right, these are the formulas. These ones you should put in a box somewhere and remember. This is how you handle antiderivatives of exponential functions. Let's just do a simple example. All right, 3 quick examples. I changed the names of the variables just for fun. You know the textbook likes to do this. For the first one, I used the rule that I just erased about e to the kx, because where the k is 3, right? And the x is called t in this problem. How do you handle the 7? Remember, if you have a constant multiple inside the integral, that constant multiple just is a constant multiple in front of the answer. So the 7 will just stay like it is. And then on e to the 3t, I use the e to the kx rule, and I get 1 over 3 e to the 3t plus c, right? That was the e to the kx rule, where k was 3, and you know, in this example, the variable is called t instead of x. Okay, great. What about this one? All right. Here I have a 3 down here. It's not an e. I'm using the a to the kx rule, where the a is 3 and the k is minus 2. I get 1 over minus 2 ln 3, 3 to the minus 2x plus c. This is just directly plugging into those formulas. All right, and finally, let's do this one. This one is a little harder, I suppose, because it has 2 parts. The first part is a e to the kx. The second part is something else. But anyway, let's do the first part. The first part is a e to the kx. I get 1 over k, which is 3 in this case. E to the kx. Now, it's not called x this time. It's called u, but whatever. This is the e to the kx rule. And then I go plus. How do you handle u to the minus 2 power? Actually, this is a little blast from 10 minutes ago. This is not an exponential function. We don't have the variable inside the exponent. This is a power of x, right? Or it's a u in this case. But you handle that like any power. You increase the power by 1, then you divide by the new power. What about the 7? The 7 just stays as a 7 coefficient in the answer. So it becomes 1 over minus 1 u to the minus 1 plus c. There you go.